When beta-carotene is oxidized in vivo, it breaks in half and forms molecules of retinal, vitamin A, which is a precursor to the pigment in retina responsible for vision. The conjugated system of retinal consists of 11 carbon atoms and 1 oxygen atom. In the ground state of retinal, each level up to n equals 6 is occupied by 2 electrons. Assuming an average internuclear distance of 140 picometer, calculate the separation in energy between the ground state and the first excited state in which one electron occupies the state with n equals 7 and the frequency of the radiation required to produce a transition between these two states. How does the absorption spectra of linear molecules shift with number of conjugated atoms? The structure of beta-carotene is given. So we can see that beta-carotene is conjugated, but the problem is concerning with vitamin A or retinal. This is the structure of retinal. If we count the number of conjugated atoms, we can start from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 atoms involved in conjugation and there are 11 bonds. So to solve this problem, we need not know the structure of retinal because all we need to know is the number of atoms in conjugation and the number of bonds in between them, which is given to us. Any conjugated system can be modeled as a one-dimensional particle in a box. This is because the conjugated system is linear, so we can assume that it's a one-dimensional. For one-dimensional particle in a box, energy is given by E equals h squared n squared by 8ml squared, where L is the length of the box, m is the mass, and n is the energy level. And h is Planck's constant. The ground state of retinal, each level up to n is equal to 6 is occupied by 2 electrons. We have to find out the separation in energy between the ground state and the first excited state when the electron occupies n equals to 7. Highest occupied level is n is equal to 6 in the ground state. In the excited state, n is equal to 7. So we have to find the difference in energy between the n is equal to 7 state and n is equal to 6 state. So delta E will be equal to E of n plus 1 minus E of n, which is h squared n plus 1 squared by 8ml squared minus h squared n squared by 8ml squared. If we take h squared by 8ml squared outside, we can have n plus 1 squared minus n squared. This will be n squared plus 2n plus 1 minus n squared which is h squared by 8ml squared times 2n plus 1. So this will be the delta E between E of 7 and E of 6. H is Planck's constant. which is 6.626 times 10 to the negative 34 joules second. Mass of the electron is 9.1094 times 10 to the negative 31 kilograms. Energy level is 6, which is the highest energy level of the ground state. The average internuclear distance equals 140 picometer. Since we have 11 bonds and the distance of one bond is 140 picometers, the distance of 11 bonds would be 11 times 140 picometer. The length of the one-dimensional particle box would be 11 times 140 picometers, which is 11 times 140 times 10 to the negative 12 meters, because 1 meter is 10 to the negative 12 picometers. This gives us 1.54 times 10 to the negative 9 meters. Now we can plug in the values. E equals h squared, which is 6.626 times 10 to the negative 34 joules second, times 2n plus 1, which is 2 times 6 plus 1, over 8 times 9.1094 times 10 to the negative 31 kilogram, times 1.54 times 10 to the negative 9 meters squared. Solving for this gives us joule squared second squared over kilogram meter squared. Okay. Let's look at the units. Joule is units of energy, which is force times distance. Units of force is mass times acceleration. So units of joule is kilogram meters per second squared times meters, which is kilogram meter squared per second squared. Now plugging this into this, we get kilogram meter squared per second squared, the whole square times second squared divided by kilogram meter squared. This gives us kilogram meter squared per second squared, which is the unit of joule. So we get 3.30 times 10 to the negative 19 joules. The second part of the question is, we have to find the frequency of the radiation required to produce a transition between these two states. To find that, we can use E equals h nu, where nu is the frequency. So the frequency of radiation required to produce the transition between the two states would be delta E. So nu equals delta E over h. By substituting the values, we get 3.30 times 10 to the negative 19 joules over 6.626 times 10 to the negative 34 joules second. This gives us a value of 4.98 times 10 to the negative 14 per second. How does the absorption spectrum change with the number of conjugated atoms? We saw that delta E equals h squared over 8 ml squared times 2n plus 1. So we can see that as the energy level increases, delta E increases, and as the distance of the one-dimensional particle box increases, the energy decreases. The distance of the one-dimensional energy box is directly dependent on the number of conjugated atoms. So if the number of conjugated atoms increases, delta E would decrease. Since delta E and frequency are directly proportional, we can say that as number of conjugated atoms in the system increases, the frequency will decrease. Two different conjugated systems with length L1 and L2 such that L2 is greater than L1 because L2 has greater number of atoms in the conjugation than L1. Let's look at the waves in the energy levels. If this is n is equal to 1, n is equal to 1 will have 0 nodes because number of nodes is energy level minus 1. So n is equal to 1 will look like this for L1, and for L2 it will look like this. If you come to n is equal to 2, it will have 1 node, so that will look like this for L1, and for L2 it will be like this. Similarly, for n is equal to 3, you have 2 nodes, so it will be like this. And here, like this. So we can see that as the length of the conjugated system increases, the wavelength is increasing and the frequency is decreasing. The particle on a ring is a useful model for the motion of electrons around the porphyrin ring, the conjugated macrocycle that forms the structural basis of the heme group and the chlorophylls. The group may be modified as a circular ring of radius 440 picometers with 22 electrons in the conjugated system moving along its perimeter. In the ground state of the molecule, each state is occupied by 2 electrons. Calculate the energy and angular momentum of an electron in the highest occupied level. Calculate the frequency of radiation that can induce transition between the highest occupied and lowest unoccupied levels. There are 22 electrons in the conjugated system, which means there should be 11 pi bonds. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is in the form of a circular ring like this. So we can consider the motion of these pi electrons in the circular ring, and the radius is given as 440 picometers. Since there are 22 electrons involved in the conjugation, and there should be 22 divided by 2, which is 11 pi bonds. Because there are 11 pi bonds, (11 over 2 is 5.5, and when you rounding it down, you get 5. So we can say that the angular momentum states will have quantum numbers equal to m's of L being 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and plus or minus 5. Since each orbital can occupy 2 electrons, we can see that m's of L will have 2 electrons. When m's of L is plus 1, it will have 2 electrons. When m's of L is minus 1, it will have 2 electrons, so that would be 4. Again, when m's of L is plus 2, it will have 2 electrons. When m's of L is minus 2, it will have 2 electrons, so it will be 4. So 4 here again, 4 here, 4 here. If you add them up, we see that we account for 22 electrons. The energy required for transition would be the energy required for transition between the highest occupied angular momentum state, which is m's of L equal to plus or minus 5, to m's of L is equal to plus or minus 6, which is the lowest unoccupied state. So this is the highest occupied state, which is m's of L equal to plus or minus 5, and this is the lowest unoccupied state. Note that the energies in m's of L of plus 5 and m's of L of minus 5 is the same. They will be degenerate, and m's of L of plus 6 and m's of L of minus 6 will also be the same because they both are degenerate. So energy in m's of L of 5 is given by E equals L squared H cross squared by 2I, and I is equal to mr squared, where m is the mass and r is the radius. So to find out the energy and angular momentum of an electron in the highest occupied level, first let's find out the angular momentum at the highest occupied level. The angular momentum is given by J of Z is equal to m's of L H cross. In this case, the angular momentum of the highest occupied level is 5. So for the angular momentum quantum number of the highest occupied level is 5. That times H cross, which is 6.626 times 10 to the negative 34 joules second, over 2 pi, which is 2.314. That gives us 5.273 times 10 to the negative 34 joules second. So this is the angular momentum of the highest occupied level. Of the electron in the highest occupied level would be E is given by H cross squared L squared by 2I. So that is 6.626 times 10 to the negative 34 joules second over 2 times 3.14 square times 5 square over 2I, which is 2 times 5.273 times 10 to the negative 34 joules second. We get 7.88 times 10 to the negative 19 joules. For part B, calculate the frequency of radiation that can induce a transition between the highest occupied and lowest unoccupied levels. We have to find delta E between m's of L is equal to 6 plus or minus 6 and m's of L equal to plus or minus 5. So since E equals L squared H cross squared over 2I, we can say that delta E would be equal to those times m's of L final squared minus m's of L initial squared. So that would be H cross squared by 2I times 36 or 6 squared minus 5 squared. Plugging in the values, we get 3.46 times 10 to the negative 19 joules. The Bohr frequency associated with this delta E will be delta E is equal to H nu. So nu would be 3.46 times 10 to the negative 19 divided by 6.626 times 10 to the negative 34 joules second, which is 5.23 times 10 to the 14 per second.